Sorry? Oh, it's a great pleasure to have with us Professor Terry RUDOLOH. He has done very important work in different areas of quantum information, quantum computing, aspects of quantum mechanics, and he has been at Imperial College for quite a few years, doing great work there. So I'm doing a very exciting new quantum computer that he's going to describe to us today. Okay, thanks for being with us.
Thank you, Franco, and thank you everyone for having me. I hope you can hear me all right. It's quite late, and yeah, just interrupt me if I'm not coming through properly, or ask me questions if you want to. Yeah, so I'm going to talk to you today about quantum computing, and I'm going to talk to you about quantum computing with light, with photons. And I, you know, have been doing this now for 6 years, 7 years. And in fact, the last time I was in Kigali was, I think, just before I started doing this in this company. I was writing my book, QA6-Third, and we just started this company. And now it's quite far down the road. And yeah, it's a lot to tell you about. But so, yeah, I want to talk to you about quantum computing, and I'm going to start by talking about just sort of abstract quantum computing, and then abstract quantum computing with photons. And so I guess the best place to start is idealized classical computing. Like, what is a computer? And in the figures I'm going to show you today, almost always time is going to run vertically on the page. And, you know, here's a sort of the kind of thing you might have seen if you did an undergrad in engineering or electronics or something. A kind of description of a classical computer as a network in which you input classical bits. The input bits, we think of them abstractly as zeros and ones. Physically, they're like some state of a system. There's some configuration of the world, of electrons. And then as time goes on, that state evolves and you go through gates. So here you see a bunch of NAND gates and OR gates and so on. And then you get out the answer to the computation. And a quantum computation is typically presented as pretty much the same thing. So here's, like, you know, an abstract view of a quantum computation. I have some input qubits. So I don't know if you guys can see my cursor. I guess that's kind of important. Let me see if I can do this. So hopefully you can see this.
The cursor, yeah.
You can, okay, great. So this here is my picture of a qubit. It's just sort of an atom. And, you know, the naive version of quantum computing just says, well, I'm going to replace every classical bit by a quantum system, a quantum bit. And I'm going to replace every classical gate by some kind of quantum gate, some sort of evolution between two quantum bits. And then I get out some output qubits as time goes on. And if you look at the quantum state of that system, then in a sort of abstract mathematical sense, you can think of it as a big vector in some kind of space, a Hilbert space, and that vector evolves smoothly through that space. But then at the end of the day, you've got to measure the output to the computation. So you need to get some classical data. Why? Because we are classical beings, and for a computation to be useful to us, we need some classical data. And so, you know, in the simplest version of quantum computing, I just replace the classical bits by quantum bits, the classical gates by quantum gates, but I need to make sure I have classical input and output to the whole thing. Now, that seems like an easy enough thing to build. The problem is the following, that right now, if you want to do a useful quantum computation, if you want to do something which, we can prove that we know for sure is going to be useful, then you need to do billions of those gates. So this kind of figure that I drew here is very naive and simplistic. This is sort of 5 qubits doing, a handful of gates, 8 gates or something. But actually, to do something useful, we need to be able to do billions of these gates. And we need to do billions of these gates, even if everything works perfectly. Okay. So what you're seeing in this figure here is the size of the computation, and this is of the ideal computation versus the date. Okay, so quantum computing started somewhere over here in the mid-90s, and this is the size of the computation. So it's the number of qubits times the number of gates, basically. And here are some algorithms. This is factorization, if you want to run Shor's algorithm. Here are some algorithms to do with stock market pricing. Here are some algorithms to do with simulating quantum systems, simulating condensed matter systems. And what you see is that you need to be able to do very large numbers of qubits and gates, even if everything is working perfectly. And unfortunately, in the real world, stuff doesn't work perfectly. And so we have an even larger overhead to do with the fact that we need to do error correction. So because the qubits and the gates that we use are not perfect, we actually have to build in redundancy into them, and we have to do a very complicated procedure that we call fault tolerance in order to be able to run anything that's useful. Now I see some chats in the window. I don't know if someone wants to ask questions or interrupt with questions, that's fine. But maybe one of the moderators can do that for me. That can moderate that for me. Okay, so let me just take that off, kill that. All right.
For the questions, typically it's done afterwards. So you have like 30 minutes and then 5-minute questions.
Okay, that's good.
So go ahead.
Okay, cool. Awesome. Okay, so what we learn from a figure like this is that we're going to need to be tolerant to faults, because the problem is the following. Let's say you build a system that has a 1 in 100 error. That's fine, but if you're going to do many more than 100 operations, well, then you're almost certainly going to have an error. Okay. And the other thing we learned from this is that no matter what you build, it's going to have to be very big, and humans cannot do anything on this planet which involves building billions or tens of billions of systems, unless it's manufacturable. And by manufacturable, I mean manufacturable in a standard process by which we build things like current computers, transistors, silicon chips, and so on. Okay, so is this advance? Here we go. So here's the thing. Right now, there's essentially 2 extremes of how to do quantum computing when you have errors. So if in a non-idealized world in which, when things go wrong, there's sort of 2 extreme things that you can do. So most of the world, like most of the world of superconducting qubits, for example, is involved with the thing on the left here, which is what we call circuit-based quantum computing. That's when you have a static array of qubits. So here's like my matter-based qubits, we would call them. And in this world, you have the ability to do unitary gates that entangle qubits adjacent to each other. There's a completely different approach to doing non-idealized quantum computation, or what we call fault-tolerant quantum computing. That's called the cluster state approach. And in this approach, you actually start with entanglement. So over here, we start with no entanglement over in this sort of more extreme approach, we start with a large amount of entanglement. And the big difference here is the following, that in the approach on the right, we start with entanglement and we actually destroy it with single qubit measurements. And in the approach on the left, we start with no entanglement and we actually create it with entangling measurements. Both approaches need measurements, and the reason is that when you have a noisy computation, you have to remove entropy, and removing entropy in quantum systems always involves doing measurements. Okay. Now, the approach I'm going to talk to you about today uses photons, and with photons, we can't do entangling gates very easily. And the reason is that photons don't actually interact with each other. So despite what Star Wars might have told you to believe about light, photons just pass through each other. Take two torches, you know, sadly, it's not easy to build a lightsaber. And so historically, in order to deal with the fact that the photons themselves are not, don't interact with each other, there've been two approaches to do with the two approaches to dealing with imperfect quantum computations. The one approach has been called KLM, and it was the first approach discovered. And in that approach, you find ways of doing gates by what we call gate teleportation. And we can boost the probability of doing an entangling gate between two photons, close to probability 1. At the other extreme was something that I worked on in the mid-2000s, I guess, which is to generate one of these initial entangled states up front and then do single qubit measurements. So on photons, it's possible to do single qubit measurements. But what I'm going to tell you about today sort of lies somewhere in between, and it's what we call fusion-based quantum computing. And so this is really the key to how we do photonic quantum computing at PsiQuantum. So in fusion-based quantum computing, we start with fixed amounts of entanglement, a small entangled, what we call resource state. The size of that state does not grow with the size of the computation. And then we do 2 qubit measurements that we call fusions, which are basically like a probabilistic Bell state measurement between the qubits. And I want to give you a sense so that you go with at least some new physical content as to how these measurements work, and they're extremely simple. Okay. And basically what I want to give you a high-level picture of at first in this talk is how it is that the fusion-based quantum computing lies somewhere in between this sort of standard approach that most companies are following and this cluster state approach that I think is like conceptually very different. Okay. So in order to understand a bit of this physics, you first have to understand how it is that we build qubits out of photons. And the way we do it is as follows. We take a piece of, in this case, silicon or silicon nitride, a piece of semiconductor, and we have channels cut into it, waveguides. And we have a photon that is constrained to just travel, to propagate along that waveguide. And if you design the shape of the waveguide and the size of it properly and you choose the photon right, it actually gets confined into this sort of channel. And it gets confined actually to sort of sub-wavelength, like it's sort of smaller than the wavelength of the light, in fact. And the way we encode a qubit is that if the photon is in this channel, it's the qubit state 0, and if it's in this channel, it's the qubit state 1. And then we can build sort of etch into the waveguides, bringing them closer together. That causes there to be some tunneling between the two waveguides. That does a sort of non-trivial coupling of the two states here. We can do phase shifters, we can do more non-trivial couplings, and we can create superpositions of just a single qubit in a very simple system like this. Physically, it looks something like this. So this here is an actual electron microscope image of such a thing. Here are the channels. Here's where we bring them together. They go apart. You can sort of see the scale here. This is about 25 microns. But the point is that we can build this in the same kind of manufacturing process that we build laptops and cell phones. And so we can build billions of these things. And you can see where the light sort of comes together. There's actually a gap that you can't quite see here. But this process, it turns out, although I've drawn it here as a single qubit operation, turns out to be enough to do an interaction, and I use inverted commas because it's not really an interaction between two qubits. And this interaction between the two qubits is what we call fusion. And the fusion is the equivalent for photonics of the C0 gate. It's the simplest, non-trivial thing we can do that couples together two qubits. And so I want to explain to you how that works. And it's reasonably simple physics. So here are two qubits. So again, time is going to run down the page now. These are two of these waveguides that are sort of etched into the silicon, and qubit 1 basically means a photon is either here on the left, which would be the state 0, or it's here on the right, which is state 1, and qubit 2 has a different photon, which either here on the left is state 0 or here on the right is state 1. And then, like in the figures I just showed you, obviously it's a bit more schematic, we can bring the two waveguides close together, and then we can do a photo detection. That's what these green things are meant to depict. And similarly, we can bring these two waveguides close together and do photo detection. And now let's ask what happens, or what can we deduce about the quantum state of these two qubits, so qubit 1 and qubit 2, if we happen to detect, for example, one photon here and one photon here. Okay. Well, if we detect one photon over here, because we've coupled these two waveguides together in a tunneling phenomenon, we cannot deduce, did that photon actually come from over here? In which case, qubit 1 was in the state 1, and qubit 2 was in the state 0, because there was no photon coming from here. Or is it the other way around, that qubit 2 was in the state 0? Like, did the photon come from this qubit 2 over here, or did it come from this qubit 1 over here? We can't tell. So we've coupled these together in a way that we've erased the information as to where the photon originated. And similarly, by detecting a photon over here, we don't know, was it from this qubit? Did it come down here, or did it come from here and come down here? And so if we look at, like, what is the quantum state of the two qubits that could have caused this particular detection pattern, we don't know. Was it qubit 1 in the state 1, 0? So this is one photon in vacuum, and qubit 2, one photon in vacuum, or was it qubit 1 in 0, 1 and qubit 2 in 0, 1? We don't know. So writing that as a qubit state, we don't know whether two qubits were both in state 0, like did they both have photons here, or did they both have photons here? Were they both in state 1? Or if you're into, like, the stabilizer language of quantum mechanics, we don't know, you know, what we basically learned from this detection pattern are two bits of information. It's like, what are the values of the stabilizers? Are the XX values 1 or -1, or the ZZ values 1 or -1? So what we've actually done is a non-trivial measurement. We haven't actually interacted the photons. What we've done is done an interference experiment in such a way that we've erased the information as to which of the qubit possible states we had, and that turns out to do an entangling measurement on the qubits. Now, we like this measurement a lot. We call it fusion. We like it because it's extremely fast. The photons move fast. The detectors respond extremely quickly. They're very clean. We're removing a lot of entropy when we do this measurement. As I showed you some pictures before, it's very manufactured. You can just build huge numbers of these. You know, like this is the equivalent of our C0 gate, and we can build billions of these C0 gates. There's some more subtle things about why we really like this measurement. It's extremely phase stable. It has a heralded error. So if we don't detect a photon, we kind of know, hey, I should have seen a photon there and I didn't. Okay. But it has some downsides. So the downsides are the following. One is that we've destroyed our qubits. Like, how can you do a computation if you've gone and, absorbed in some detector the photons that you had? And the other is that it's probabilistic. It only succeeds if I find one photon up here and one photon down there. If I find both photons down over here, well, then I know it must have been that qubit 1 had the photon here and qubit 2 had the photon here, in which case I projected onto the product state of qubit 1 being in state 1 and qubit 2 being in state 0. So it's a probabilistic measurement, doesn't work every time. All right, so back to this sort of high-level picture. The way we do fusion-based quantum computing is we want to use these fusion measurements, and despite the fact they're probabilistic and destructive, we want to be able to do a fault-tolerant computation. Okay, and how does fault-tolerant quantum computing look? Well, I'm going to give you now a very, very much a theorist's version of how fault-tolerant quantum computing works. And this is really the version, if I stepped away, someone put a fault-tolerant quantum computer in front of you tomorrow, what would it look like? And now imagine you can't see quantum systems. So how does a fault-tolerant quantum computing look like if you can only see the classical information in the computer? Well, the classical information is a whole bunch of bits, right? It's some classical bit, zeros and ones. And if you couldn't see microscopically what's going on, you would just see a whole bunch of zeros and ones. And so I want you to think of this cube as a volume of space-time with a whole bunch of classical bits, zeros and ones. So think of time as going this way and space as this way. And someone has built a fault-tolerant quantum computer and they just like plonked it in front of you. And you can just see these classical bits. How would you know that this thing was doing a fault-tolerant quantum computation? Well, originally, when you looked at these bits, they would look random. A whole bunch of, locally, they would just look like zeros and ones. But if you started looking more carefully, you would find that around cubes in these classical bits, there would always be a parity of 0. If you added up all the sum mod 2 of all the qubits, of all the classical bits on the faces of these cubes, you would always find a parity of 0, or most of the time find a parity of 0. The sum mod 2 of 0. And as you ran through this volume, you would find that almost all the time you were seeing a sum of 0, but occasionally you were seeing a parity of 1. That would look like a kind of little weird, noisy defect in this set of classical information. And then as you ran through even more, you would occasionally find some sort of weird boundaries, some sort of dislocations in these classical bits, a sort of point where this summing up these cubes actually skipped half a lattice site or something. And I've tried to draw that as like a blue surface over here. And if you knew nothing else microscopically, if you just could see these funny correlations that most of the time sum to mod to 0 mod 2 and then sometimes have this funny dislocation, you would actually be seeing what we call the topological fault-tolerant quantum computation. And the qubits of this topological fault-tolerant quantum computation have nothing to do with the microscopics of what's going on. They actually are governed by these large membranes of what are called logical correlations, of these funny sheets of dislocations in the classical information of this computation. So it's kind of an amazing thing, and I'm still learning about it 5 or 6 years later. But this is how you would be able to spot that a fault-tolerant quantum computation was happening. Now, if you could look microscopically, you would say, well, where does this classical bit come from? And if you're like Google or IBM or someone who's doing a superconducting qubit approach to quantum computing, the origin of that classical bit would be something like the following. It would be like, well, this classical bit 1 actually originated from, I had a whole array of qubits, like these are matter-based qubits, maybe ions or superconducting qubits, and I put them through this quantum circuit. Over here is a quantum circuit that has an ancilla qubit and 4 data qubits, and you run the qubits through the circuit, and then you do a measurement on this ancilla qubit, and then this classical bit 1 is just the outcome of the measurement on this ancilla qubit. Okay. So that would be like microscopically what was going on. And if you were doing a cluster state computation, the other extreme of fault-tolerant quantum computing that I talked about, where somehow you built a large entangled state and then did a single qubit measurement, then the origin of this classical bit 1 would just be the outcome of one of those single qubit measurements. Okay. And in what we do with photons, the outcome of that measurement is the kind of thing I just showed you, where we had a bunch of detectors and we saw some photons click. It's the outcome of a fusion measurement. And so these classical bits, we create them by making some small entangled states of photons, spreading those entangled states of photons in space-time, and then doing this fusion measurement, which is actually this very simple, like, bring the waveguides together and put a photodetector there. I guess what I'm trying to get at with this is that all of these approaches to quantum computing are the same once you get to the level of the fault-tolerant correlations that produce the logical qubits that make your fault-tolerant quantum computer. It's a bit like violating a Bell inequality. It doesn't matter which physical system you do it with, as long as you produce the right correlations, you have a way of doing, fulfilling the task that you want. And so in our case, yeah, we do it in a slightly different way. We produce a different entangled state of the photons and we arrange them in space-time in a funny way. But at the end of the day, we're just doing a standard fault-tolerant quantum computation. Okay. So that's like a very, very abstract way of thinking about doing a quantum computation when you have errors. Here's a slightly more, but still a theorist version of this approach. And we call this approach fusion-based quantum computing because it involves this fusion measurement. So the slightly more concrete version of this is as follows. Imagine we have a piece of hardware, whatever it is, that let's say every nanosecond, so running at about a gigahertz, can produce 6 entangled photons. Okay, so here are 6 different photons. Here's a particular entangled state, doesn't matter so much what it is. Okay, each one of these photons is made from 2 waveguides, exactly like I showed you before. So the 0 and the 1 state is the photon over here or is the photon over there? Okay. So imagine this as like 12 of those waveguides running through a piece of silicon. And then the way we fill up the space-time with those classical correlations looks something like this, very abstractly. So if you imagine each one of these gray squares just produces one of these entangled states, so that's one of these 6, these sort of hexagonal entangled states here, then these little yellow flashes are doing that fusion measurement, the thing I showed you before, which was bring the 2 waveguides together and do the detection. Then what are we getting out of that? Well, we get a bunch of data, and that's what these classical bits over here represent. So we're just getting out a whole bunch of classical bits. Okay, so we're just spitting out these resource states, doing these measurements, these flashes. Each flash gets turned to a classical bit, and then we basically filled up space-time with a whole bunch of classical bits. And what we've proven is that if we do this the right way, we fill space-time up with just the right set of correlations in those classical bits in order to be able to do this topological fault-tolerant quantum computation. Okay? So you can sort of think of it that block that I showed you before of space-time, that's what we're getting out of this thing over here. Now, in fact, what we do is even a little bit more subtle than this. And I think it's really cool. I'm going to try and give you a high-level picture of it. So we make use of something that we call interleaving. And this is something which is available to photonics. I don't think it's really available to other approaches, but it's kind of neat. And I think it's fun to have a high-level picture of what's going on. So interleaving is the following. Imagine I have some device that can spit out these entangled states of photons. Okay. So we call that a resource state generator, RSG. And then that I have some way of delaying the photons with a delay. Now, in actual fact, the delay that we use is a piece of optical fiber. So the photon comes out, we put in a fiber, and then it sort of sits in this fiber for some number of time steps, and then it comes out. So over here, this means there's a delay of 900 clock cycles. So if we're running at a gigahertz, this is a delay of 900 nanoseconds. This here is a delay of 1 nanosecond. This is a delay of 30 nanoseconds. And so we build a module like this, and it looks a little bit complicated. So we've got this thing that spits out this entangled state. We've got some delays. We also have some switches here that let you decide, is a photon going to go into the delay, or is it going to be fused with some other photon? So the F here is the gate I showed you before, where we just bring the waveguides together and we do the detection pattern. That's a fusion device. We have a bunch of delays, and we have one of these modules. And you might think that we build many of these modules, but we actually play the following trick. We connect the module back onto itself. So it's like a self-interacting module. And by doing this, we get the effect that you can see on the right here. So what I have here is, instead of having a whole array of these resource state generators, I now just have a single one of them, but I have some optical fibers connecting the resource state generator to itself. That's what these red lines over here mean. They're sort of pieces of optical fiber that reconnect the thing to itself. And now what we're doing is a kind of 3D space-time printing. Instead of producing that block of classical bits from many resource state generators operating at, on the same clock cycle, I'm taking one of them and I'm running through space-time, and I'm sort of printing out these classical bits. Okay. And this leverages the sort of miracle of optical fiber, which is an extremely good delay for quantum systems. And once again, I'm producing the same block of fault-tolerant classical correlations that allow us to do this computation in ways that, are very complicated. It takes the whole PhD to really understand this kind of thing. But I think it's kind of miraculous that we're able to build it in this very simple way. So that hopefully gives you an idea of, how it is very abstractly that we're trying to do something with photons that at some level is very similar to the way that other approaches go, and in some ways is extremely different. Okay. And so, the sort of summary of that would be, with photonic qubits, we can do a whole bunch of long-range connectivity because we've got optical fiber. We can build the stuff very simply in a fabrication facility, the same kind of place that builds laptops and cell phones. That's very easy for us. We can make, billions of these things and do. But actually for us, the hard part with photons is creating that initial entangled state. Whereas for other approaches to quantum computing, what we call matter-based qubits, the problem's inverted. It's kind of easy to entangle matter-based qubits because the electrons have charge, they want to talk to each other. It's actually sort of hard to not have them talk to each other. With photons, don't want to talk to each other. But with matter-based qubits, the other parts are much harder, I think. Okay, so the story I've told you so far, has all been very idealized models of classical and quantum computing. I've given you this kind of zoomed out view of fault-tolerant quantum computing, tried to give you a little bit of a space-time view of it. I just want to finish by giving you some pictures of, what is it going to look like sort of physically, and how do we know, how do we have the confidence that the thing that we're going to build works? Okay. So what is it going to look like? If you've ever been to a university optics research lab, it looks something like this. It's like a laser table covered with, optical elements and a bunch of fibers, those optical fibers connecting things, and detectors and lenses and lasers and stuff coming in. That is not the way you can build a machine that has to have, like, there's no way that this machine has, less than hundreds of billions of components. Okay. So like, this is just not a scalable technology. The kind of thing that we build looks more like this. So this here is a wafer of silicon. It's being manufactured the same kind of place that builds your laptops. It involves, in this case, I guess, close to 1,000 process steps. And we make silicon chips on this thing that have thousands of components, and then on a whole wafer we have tens or hundreds of thousands of components. So every chip over here is equivalent to hundreds of university research labs of this kind of form. Okay. And then we have to manufacture these things, and we can't. We're building big machines with all these components. We can't just have grad students going into the lab and testing these things. So we essentially have to have robots that take in. So this here is a whole wafer, a 300 mil wafer of these kind of components. We load them into automated machine that takes them and drops them down. I used to have a video of this, and it doesn't work in this PowerPoint anymore. But sort of drops it down, a robot goes in, injects light, and measures these things, because obviously we're building millions or hundreds of millions of component devices. We can't measure all of them, so we do a bunch of statistical sampling and check, hey, do we really know what's going on? Does this design work? And then we iterate on the procedure for manufacturing these things. Right? So it's very much an automated manufacturing scale process, but it kind of has to be, because as I showed you at the beginning, even if everything worked perfectly, we need to be able to build machines that are capable of billions of gates. Because of the issue of fault tolerance and error correction and so on, you've got to be able to deal with sort of hundreds of billions of component machines. Okay. Now, to be a bit more concrete, we actually build two types of chips. We have a photonic chip, which has all those waveguides and the detectors, the kind of stuff I showed you before. But then we have to bond on top of it an electronic chip, which does all the control for the stuff that's going on below. It does some logic. It decides, hey, are you going to switch this photon to go over there? Or are you going to make it come back here? Or are you going to block it? Or are you going to, adjust some phase shifter or whatever it is? So that logic is done by an electronic chip. And because the wavelength of the photons that we use is actually quite big by comparison to electronic transistors, we can put a very large number of control systems right on top of our photonic chip. It's sort of a very fortuitous circumstance where we can put these things very close together. And because photons as qubits, they don't feel heat, it doesn't matter that we put this kind of hot chip so close to the photons. Okay. We also have to have a way of networking these things. And, we're very fortunate with photons that the issue of networking was solved by people who were interested in doing classical communication and optical fiber technology. We need to have slightly better connectors than they do, but the optical fibers that currently are conveying what I'm talking to you about, they're good enough for what we're doing. So this is what we build, like kind of packaged things. This is a very old picture of one of these kinds of things. We now have much more sophisticated chips, but here you can see a chip with a bunch of optical fibers coming in and out. And unfortunately, we do have to cool these chips because our single photon detectors need to be cold. But what we're building, we don't need to cool the qubits. The qubits can be warm. It's just the photodetectors that need to be cold. Okay, so now I've told you a whole world in which you have these beautiful components, and for me as a theorist, I can design the system and say, this is what my dream system looks like. And I send it off to our engineers, and the engineers come back and this is what they bring me. Okay, they bring me some kind of approximation to the thing that I would like. And so what we want to know, of course, is like, how good does this thing on the right need to be in order to, be a good approximation to the thing on the left so that the whole thing will work? And for us, that means we first got to identify all the things that can go wrong in the system. So here, with the hamburger, there's only 10 things that can go wrong. But in our quantum computer, there's sort of on the order of 40, I guess, constraints or things that can actually sort of go wrong in the system. There's sort of the key errors or the key imperfections in manufacturing. You can list them all. Here's some of them. And so what we want to know is when we build our system and we get the squashed hamburger on the right, is it going to work or not? And the way we deal with that is actually something which has taken, a team of, I guess, about 30 people, many years to build. We have a whole simulation stack. So we have this very detailed modeling that starts at the component level. So if it's a photonic component, it might be some finite difference time domain modeling, or it could be some thermal modeling, it could be like electronic modeling. This is the kind of stuff that is done in the silicon engineering world in extreme detail. We have to start with some sort of extreme engineering modeling of the stuff we're building. And then we have to look at the quantum versions of these things over here. So we have to say, well, what happens when I take these systems and I have to model the generation of quantum states of light in them? And then I have to lay them out in circuits. And so at this point, you get to a point where you can't just throw a classical computer arbitrarily at the problem, because this is a quantum system. Classical systems can't simulate quantum systems. So we have to have a whole simulation stack that can simulate these photonic circuits. Once we can simulate this sort of generation of small amounts of entanglement in these photonic circuits, we have a whole different simulation stack that looks at combining this entanglement to make larger photonic entangled states, the things that I was showing you before called resource states, like the ring of 6 entangled photons. And we want to do that in a kind of robust, noise-resistant way. We then, at this point, our photons have become qubits. So over here, our photons were just sort of general multimode states of light. Over here, they become qubits. We then have a different simulation stack, which takes in the photonic qubits and all of their noise and imperfections and says, well, if I lay them out in space-time in a particular way and I do those fusion operations, then am I going to generate the right entanglement that I fill up space-time with the right correlations that I can do this fault-tolerant quantum computation? So there's a simulation stack like that. And then we have a final simulation stack that's, maybe another group of 6 or 7 people, which really look at what's the optimum way to use these correlations to run a genuine quantum computation. And this stuff here, a lot of this is very new. I don't think anyone else has ever really taken these fault-tolerant simulations all the way up to these logical gates like this. But we now live in a remarkable world where, our team is able to look at some imperfection, some engineering imperfection that says, look, the variance in the roughness of the waveguides that the photons are propagating down, this foundry has a larger variance than we thought, and run it through this whole simulation stack, and we can say, like, hey, here's the impact of that imperfection over here on this logical qubit, which is actually comprised at the end of the day of many tens of thousands of photons that sort of at the end of the day ended up being part of this logical gate. So it's quite a remarkable thing. It's been an incredible tour de force to put all of this stuff together. We're continually adding to it, developing it, letting it take into account more more ideas we have for improvements and things that make the whole game more robust. But this is my single slide version of what's going on. Okay, so it takes real people to do this kind of thing, and what I've shown you is very much biased to what I, as a theoretical physicist, understand and how I think about what we're doing. There's actually many, many different teams involved in doing this whole process. So I really talked to you about the architecture, what we call the quantum architecture and the system architecture. There will be a talk by Mercedes Mena-Segovia, who leads our system architecture team, and she'll give you a much more detailed version of this sort of modularized architecture and layout and how it works. But I should emphasize that there's just the majority of this company are not physicists. They're not even people that know any quantum mechanics. They're people that know electronics or cryogenics, or they come from the silicon world. They're people who have built laptops, cell phones, hard drives. We have people who are experts in classical nonlinear optics. We have people that are experts in optical fiber. At the other end of the stack, we have a lot of people who are experts in software engineering and writing, code for both for the simulation stack and for what are we going to do with this quantum computer when we have it. So what we call applications and compiling. So it's this massive endeavor. It takes a huge diversity of skills, a huge diversity of backgrounds of people in this company to bring a new technology to fruition. And so, for those of you listening, wherever you are, if you think that you have, skills or ideas or, sort of technical abilities in things that could be useful to us, I'd encourage you to write to us and apply to us. There's certainly no requirement that people that come to us are experts in quantum physics, for example. It's really just, like any new technology, you've got to imagine that there's no single person and no single skill set that can encompass everything that's going on. So I'm going to leave it at that, and I'll just leave you with a few references to some of the papers that explain, in a lot more detail, the architecture side of what I've been talking about. And as I said, there's huge numbers of other things to be understood on the manufacturing and processing and all sorts of other things. And I'd encourage you to go listen to the talk of Mercedes, who will explain, definitely much better how the whole system is put together. So I'll leave it at that. And I guess, I'm not sure how the questions are going to work. I see a Q&A button, or is someone going to moderate questions? Yeah. Okay, so I see. Sorry?
Oh, that's okay. So
sorry,
go ahead. When you finish, then we can get the questions.
Yeah, so I'm finished.
Okay, well, thank you for the great talk. And then indeed, the Tether. It's a very interesting talk. Can you please recommend one or two good review articles explaining the technologies in your talk? In more detail, and articles, which ones are reviews there?
So, yeah, most of the stuff is pretty new, but I would say the place to start is probably this article here, the fusion-based quantum computing. So this is the very high-level view of how to do fault tolerance using measurements instead of using gates. And so I think that this is really the place to start, would be this article, fusion-based quantum computing.
Do you have any questions here in Kigali?
I have a question, but
Yes, go ahead, Franco.
Let's first get the people in Kigali, and then afterwards I can ask later on. The different
Oh, no, we
strategies
have no-
here on the quantum computing. Now, one strategy is to do like a small toy device to tell us algorithm, and then just make it larger and larger. And then while you make it larger and larger, there are problems be made. So try to get the large system. It's tricky because if you don't have the small one scaling up, it's it seems to be why not doing like a small?
So frankly, you're breaking up so much that I'm not sure I'm understanding the question. Maybe you want to type it, but I'm not sure if that's me or you. So if people in Kigali can't hear it,
It's breaking up in Kigali also.
He's breaking up in Kigali as well. Okay, so it's not me, it's Franco.
Okay. So,
so let me just try and interpret. I think your question was something along the lines of why not build the small system and then scale it up or like do something. And the reason is that fault tolerance isn't something which works by just making a smaller system better and improving it and getting to something like that. The qubits of a fault-tolerant system are nothing to do with the physical qubits. That's what I was trying to get at with this figure. The microscopics of the physical qubits in a fault-tolerant quantum computer have nothing to do with the logical qubits of a large-scale fault-tolerant machine. They're completely different things. The logical qubits are kind of essentially like extended topological quantum correlations, like Bell correlations, but in a fancy way, and don't really have anything to do with the microscopics. And so if you want to build, you know, a machine that is going to need millions of physical qubits, but only have, say, hundreds of these logical qubits that are very different, you kind of have to start with the technology you know that can be big enough to get there before you even contemplate it. And so, but before you contemplate the microscopics. And so obviously we know the microscopics works. We built many photonic qubits in the past and but you know, the key for us has been build it. Can we redo everything we did in the past, but in a way that is actually genuinely manufacturable? Like we can't have even one single thing that rate limits us because it's not manufacturable. And so, you know, the devices that we build are not small quantum computers. They're just like these sort of microscopic devices that add one classical bit into that big space-time volume of classical correlations. And that's the kind of thing we're focused on, which, you know, just doesn't have a nice interpretation as, are we building a small quantum computer and then making a bigger and adding a few more qubits and making it a bit less noisy. Like that's just actually not how fault-tolerant quantum computing can work. And that's not just for us, that's for anyone. Believe it or not, based on the things you might have heard, that is true of any approach to fault-tolerant quantum computing.
Okay, so yeah, so you kind of answered this question. The question was about building small prototypes of computers and increasing the size and seeing how the capabilities of the machine evolve when increasing the size.
Yeah, so I mean, we build, I wouldn't call them quantum computers, we build small modules that obviously we need to understand, you know, what happens as we, you know, we can, like right now, we know we can build fantastic components as individual components, but you've got to be sure that as you put them together and, you know, as you integrate things, so, you know, the saying we have are interfaces are hard. So as you interface different things, there's many challenges you have to solve, but those challenges are not really computational challenges. They're like classical engineering challenges, and you want to solve those so that you can build a very big machine. And it's just not, you know, it's just not the right way of thinking about like how to build It's like trying to say I'm going to build, I don't know, like the atomic bomb by making hotter and hotter fires. It's just not, this different physics. It's got nothing to do with how you build an atomic bomb, how you know, to build hotter and hotter fires. It doesn't work like that.
Okay, thank you very much. Two more questions. There's a question in, is it known how to optimize
Okay.
classical computing when we talk about quantum speed up in computing? So do we know how to optimize over all models of classical computing?
Not at all. It's very much, I would say, very interesting, you know, yeah, forefront of research. And, you know, I would encourage anyone who has good ideas along those lines, read the papers. Obviously, don't ignore what's been done, but I think there's a lot of, yeah, just interesting physics and computer science and things to be explored there for sure.
Okay.
And thanks for having me, everyone. It's my bedtime here, and yeah,
Okay.
fun in Kigali.
So let's thank Professor Terry Rudolph once again.
Thank you.